See, tautomers are ketoenol isomers. The name you can understand very easily. Ketoenol isomers. What is keto group? C double bond O group. What is enol group? OH group. Is it right? Understood, no? So this is the main thing what you can observe. First one is with the example you take CH3CO CH2 C double bond O dash CH3. This is called as acetyl acetone. Acetyl acetone. You know how did you get acetyl acetone here? This portion is known as acetyl group or acyl group. CH3CO group is called acetyl group. What is acetone? Can we take like this? CH3, CO, CH3. This H is removed and you have replaced it with acetyl group. Hence you call it as acetyl acetone. Are you able to understand how did you get this? Vaishnavi, admin.
So once can you repeat?
See, acetone means CH3, CO, CH3. Is it correct? Yes or no? In that, you do one thing. In the place of 3, 1 H alone you replace. This is 1 H. Correct? Now this is fully acetone. CH3, CO, CH3. What you do? 1 H is replaced with CH3CO group. What is meant by CH3CO group? This is called as acetyl group or acyl group. Understood? So H replaced with acetyl group. Therefore, the compound is called acetyl acetone. Clear? Understood, no?
Yes, sir.
Vaishnavi, are you able to follow this?
Yes, sir.
See, if I put methyl group in the place of hydrogen, it will become methyl ketone or methyl acetone. Okay, so H dash CH2, that means CH3CO CH3 is acetone. This group you replace with one methyl group, then what it will become? The same way, methyl acetone, like this. Okay, same thing. Instead of methyl, you put acetyl. Now the question is, how do you find out the isomerism means? You know very well. Oxygen is more electronegative, right? So what will happen to this? This can attract the shared pair of electron towards itself. Is it right? So this goes towards this. So partial negative charge. Carbon gets partial positive charge. Next step is the hydrogen which is present in the adjacent position. Okay, the hydrogen which is in the adjacent position. See, you wrote like this: CH3 dash C O minus, adjacent position H is there, no? Is it right? Now what it will do? This plus is coming out and attacking to this, and your bond is coming here to form a double bond. So what you will get now? What you will get? CH3 dash C double bond O, sorry, single bond OH. Here double bond CH dash CO CH3. Now can you tell me what is the difference between the first compound and the final product? Here CO group is called as keto group. OH group is called enol group. Both have same molecular formula, but keto group is converted into enol group. Hence, this is called as tautomers or ketoenol isomers. Both of you understood this? Same molecular formula, one is existing in the keto form, another one is existing in the enol form. I'll give you some more examples also. Acetone alone you take. Directly, you take CH3 dash C double bond O dash. We can take as such also, not an issue. Can we write like this? Is it okay? Acetone. Now, once again, you know very well, oxygen is having more electronegativity. Therefore, what will happen? It will attract the shared pair of electron towards itself. Hence, H plus is being taken to this. This gets plus. Now, what will happen? I am showing direct step also, you can write, no issues. But I am showing for your understanding. This is minus carbon with H will be taken. This whole thing becomes, understood, no? This is plus, H plus. Bond comes here. The rest is as it is, CH2. How do you get the last one? CH3 dash COH double bond CH2. Now tell me now, this is which group? Enol group. Enol group. And this one is keto group. Clear? Any doubt in this? Following, right? Can we take one more example? CH3 C double bond O dash CH2 COO C2H5. You know very well this compound, what do you call? Ethyl acetate, right? Vaishnavi and Admiral, you are able to understand. Now again, you know very well that oxygen is having more electronegativity. Therefore, what it will do, it will attract the shared pair of electron towards itself, gets partial negative charge, and it will attract this H plus towards itself, and the bond moves to this. I'm showing you everything in the single step. Is it understood? So what you get now? This is CH3 dash C. OH is formed here. You get a double bond. You get a double bond and carbon. Once again, H was there. COO C2H5. Okay, nothing but ethyl. So this is called as enol, and this is called as keto group, and both are having same molecular formula, and they are existing in keto-enol isomers. So the isomers are called keto-enol isomers or tautomers, and the phenomenon is called as tautomerism. Any doubt in this? So we have taken 3 examples. Are you clear? Done. This is very important. First condition, what is that? Keto is being converted into in equilibrium with enol group. And second condition is, if you are taking between nitrogen and C, I'll write like this: H dash C triple bond N can exist in equilibrium with. So how do you write this? H N double bond C with the lone pair forming the coordinate covalent bond. So this is called as cyano group, and this is called as isocyano group. Both are existing in the equilibrium, but they have 2 different structures. Interconvertible forms only. Is it? Are you able to follow this? Cyano and isocyano are tautomers here, and the phenomenon is called tautomerism. One more example is there. HONO. This is nothing but nitrite. Nitrite will exist in equilibrium with NO2 like this, nitro. Lone pair is there, will form the coordinate bond with this. So this is called as nitro form. Yes, Vaishnavi admin, are able to follow? Understood, no? See, these are the next tautomers what you should know. First one, ketoenol is very important. Many times you will come across with that, and remaining 2 also possible, nitrite as well as NO2 nitro. Okay, can we take one example here? If they are asking you identify the tautomers for nitroethane. Okay, so here lone pair was there, coordinate bond with oxygen. This is called as nitroethane. Just find out what will be your isomer now. Just now I told no, nitro will become nitrite. So CH3 CH2 ethyl as it is. Now double bond N OH, and the lone pair is forming with this. Are you clear? Okay, no. So how did it happen here is one H will come there. That is also fine. Can we write like this? If you are showing the more electronegative oxygen will attract the shared pair of electron. Then you want one H plus to combine with this. Is it right? So therefore you got OH. And how did you get the double bond formation here? This bond is moving here. Yes or no? Understood, Vaishnavi? Or you want me to explain in 2 steps?
No, sir.
Clear, right? Okay. See, just leave this as such. Okay, we don't want to do anything here. First step, oxygen being more electronegative takes this pair of electron towards itself, gets negative charge. Okay, now so we can write like this here, keeping this O minus. Okay, next one proton will be taken by this. So from here only H plus, then this bond will come to this. Are you able to understand? So now what will happen to this? CH3 dash CH double bond N, and this will become OH, and the lone pair has formed with the oxygen. Now understood? Clear? So isonitro ethane. Okay. One more name is also there. You can call it as nitroform, means nitroform. The other one will become aciform, ACI. Remember this. It can be isonitro or aci. Clear with this tautomerism? No doubts. Understood, right? Second one is just an introduction is there for you, which is known as stereoisomerism. Okay. See, what is meant by stereoisomerism? Earlier you have taken a structural isomerism only. It is not showing any three-dimensional structure. Is it right? But in other condition, what is happening is, if two or more compounds have same molecular formula, but what is different? But they have different arrangement of atoms in space. In three-dimensional arrangement is different. Okay, earlier you had only two dimension. Understood? No, nothing but they are all having the different configuration. They have the different configuration. So these compounds, what do you call? You call them as the stereoisomers. And what do you call the phenomenon? The phenomenon which will explain all the formation is known as stereoisomerism. Both of you understood this? Any difficulty? Clear, right? Okay, how many types we discussed in the previous class? It is of two types. First one is called as geometrical isomerism. So this geometrical is again two types, cis isomer as well as trans isomer. So first one is geometrical, very important. We have that in syllabus, grade 11. Optical we will do in grade 12. First one is, what is the importance of this geometrical isomer and when it will show? Right, number one is, if you are taking, see, AB will be there, and C double bond C is, the isomerism is surrounding to carbon double bond carbon. So one side you are having AB, okay, another side also you have AB. So how they are arranged? Let me take like this, C double bond C. So the geometrical isomerism is shown by alkenes. Understood? In that, what is the first condition is, you have either AB and second one is AB. So can we take like this? If you write A here, okay, later we'll take the examples and all. And on the same side, if you have A, are you able to understand? On the same side of double bond, you have similar groups. Are you able to follow? If similar groups are on same side of double bond, now you call it as transform, TRANS, transform, and the name will remain the same, but-2-in. Is everyone clear? Any doubt in this? Can I give you one more example? Okay.
Yes, sir.
Now, right. So take it as, say, bromine on the same side, okay, and hydrogens on the same side. What will be the name of this compound now? You know that this will be the longest carbon chain. So root word is eth. So numbering is from here to here or anywhere is fine. Now tell me, this is called as ethene and dibromoethene. Is it right? So which positions can we take it? 1, 2, dibromoethene. Is it right? Now is it cis form or trans form? Observe this, on the same side of double bond, what you have? Bromine and bromines, halogens are same, H and H are on the same side. So okay, no? So if the same groups are present on the same side of double bond, then you just add a cis form to this. This is called as cis 1,2-dibromoethene. Now take the same way. What will be the isomer to this? Keep one bromo here and interchange this to other position and write in the opposite side. Same thing, hydrogen also will be in the opposite side. Is it right? This is the double bond here, plane of the. So the similar groups on the opposite side of double bond. Therefore, what do you call this? Can we write a trans right now? So trans, then name will remain the same or not? What is that? 1,2 dibromoethane. 1,2 dibromoethane. So everyone understood? This is the first type, like what we have taken the condition. What is the condition? You should have A and B. Okay, and how you will write that A and B in two forms? In the first condition, place A on the same side. In the second condition, place A on the opposite side of the double bond. Understood? Any doubt in this? Okay, one example you can take. See, one group you take, that is enough. This is in the opposite direction. Okay, so this comes in the first type of formation. Second one is C double bond C, you take AX, you take, and AY. That means, what do you mean by this? There is only one similar group, not both the group. This is your double bond. Is it right? So how do you represent this? If you take C double bond C, imagine A is there and here A is there. Fine. Now put X and Y. What do you call this form? Same group is present on the same side of the double bond. Hence it will become cis. How do you make it trans now? A is this and A in the opposite side. Clear? X, Y, you can keep like this. Clear? Everyone understood? Any doubt? So second type is only you are having one group similar. Okay. So for that, let us take this example. C double bond C. Right. Now one methyl group, one carboxylic acid group. Is it right? And then H and H. Now can you identify? Just now I told you the difference in this is you have only one similar compound, that is hydrogen, like this. C double bond C as it is. Here what you have? X, AX, nothing but methyl on this. And on the other side it is COOH. Are you clear? Y means COH. H and H is same. Right. Now, what is the name of the compound? This is your longest carbon chain. Is it right? And then functional group priority order, you know, carboxylic acid starts from this 1, 2, 3 and 4. So root word is but dash 2 en oic acid. Is it right? So we know the nomenclature. And now which type of isomer is this? Simple. This is called a cis. Why? Hydrogens on the same side of the double bond. Is it right? Hydrogen is on the same side of the double bond. Similar group. Now what you should do? How to make it as a trans compound? C double bond C. Now H is here. Take it to the opposite side and write H here. Understood? No? Now the same group is present in the opposite side of the C double bond C. So you just write it as trans and the rest will be the same. Okay, no? So what we will write, this will become CH3 and here you will get COH. Don't worry about methyl and carboxylic acid group, right? So this will be trans but dash 2 in 1 oic acid. Clear? Raghav, Vaishnavi, Admiral. Understood?
Yes, sir.
Very important thing, once again, please note that this is called as crotonic acid. Cis form is called as crotonic acid and trans form is called as isocrotonic acid. Okay, common name. IUPAC name you have written. So we need to write the common name. Understood? Crotonic acid and isocrotonic acid. Right. This we have seen. Next. Can I give one more example here? Like C double bond C. Now take CH3 and this is H and this is H and H. Okay. So what is the name given to this? Yes. Propene. Now tell me, write down the geometrical isomer for propene. How do you write this? Or butene also, not an issue. You take this as propene and then you take it for butene also. Okay, like 2 carbons. Now, which type of compound is this? Can we write like this? C double bond C, A2 and AB. Yes or no? Why you wrote A2? This hydrogen is A2. Understand like that. The other side hydrogen is A and B is methyl. This will never exhibit geometrical isomerism. Okay, no geometrical isomerism if you have A to C CAB type. Clear? No? What is the reason for this? So like propene and butene you have. Okay, no? If you want to know this, see, H and H are on the same side is okay, but the problem is another hydrogen is in the opposite side. Is it correct? And here also you observe this. This is ethyl group H. But on this side, they are in the opposite direction. They are in the opposite direction, right? Are you able to follow? And here they are on the same side, right? Understood? So that's why we can't show the geometrical isomerism. Even though they are having the double bond, they will not exhibit. Understood?
Yes, sir.
Right. So first two times we have seen this is a very important thing which will not exhibit the geometrical isomerism because you are having three similar type of compounds. Clear? Now, can we see what are the properties of geometrical isomers? Okay, very important. What properties they are showing? Right. See, first one is the geometrical isomers have different physical properties. Okay, they have different physical properties like melting point, boiling point, then mu dipole moment. Are you able to understand? And then adsorption. You know what is meant by adsorption, right? In colloids and all we'll discuss. It is not absorption on the surface. On the surface, accumulation of any substance, okay, is known as adsorption, AD. If it is penetrating inside, it will be called as absorption, AB. Okay, are you able to understand the difference? Suppose you are taking hydrogenation reaction. Suppose palladium is the catalyst. On the surface of palladium catalyst, what will come and bind here? Hydrogen. Are you able to understand? Yes. This is not inside the catalyst. It is on the surface of a solid. A gas is coming and accumulating. That process is called as adsorption. Right. So these are also showing different properties in the accumulation on the surface. Clear? So they have different physical properties. First property we have discussed. Understood now? Therefore, what is the method of separation? If I have given you cis and trans isomers, and how do you separate them? What is the method of separation? Means you can use fractional distillation. You know what is meant by fractional distillation, is it right? When the boiling point difference is very low, then what you will do, you will put the fractionating column and increase the area of distillation or length of distillation. That process is nothing but fractional distillation. We will go ahead along with the purification techniques. We'll see. Okay, just you remember the methods. Okay, second one is chromatography. Chroma means color, separation of the substances using color, right? And also adsorption property is known as chromatography. Okay, everything we'll discuss. Are you able to follow? What are the first properties we have discussed? Two isomers, that is cis and trans, will exhibit different melting, boiling point, dipole moment, and adsorption. And how do you separate them? By using fractional distillation and chromatography. Clear? Understood? Second point is the geometrical isomers have similar chemical properties. That means suppose you take malic acid. One is malic acid, second one is fumaric acid. Okay, so what is the structure of that? It is nothing but dicarboxylic acid. You have two carboxylic acid groups like this. Understood? Now again this is C double bond C, well and good. On the other side you have hydrogen. Okay, so this is malic acid, and can you identify which type of isomer is this, cis form or trans form? Yes, you can easily tell, right? On this is your double bond, right, on the plane. Same type of atoms are on the same side, hence you call it as the cis form. So this is cis isomer. Are you able to follow? Now the question is, they have similar chemical properties only, we have said, but not the identical. So what is the fumaric acid structure? If you observe the fumaric acid, it will be in the trans isomer. Is it right? So how do you get that? C double bond C. If you put COOH, change the COOH to the opposite side, then it will be transform. Clear? Everyone understood this? Now they are telling they can be heated and forms anhydride. Okay, so both form anhydride on heating. Can you tell me what is meant by anhydride? Yes, what is anhydride? Yes, see, you have seen acetic acid, CH3 C double bond O dash OH, and take the second molecule of acetic acid like this. Okay, on heating, what will happen? Anhydride means removing the water, right? So acetic acid now can we write like this, C double bond O and O on the other side also C double bond O CH3. See, this is called as acetic acid. Now after removal of water, anhydride, hence you call it as acetic anhydride. Everyone understood this? Raghav, Vaishnavi, Admiral, are you clear up to this?
Yes.
Now the same thing, instead of acetic acid, now you have to take malic acid as well as fumaric acid. See, they both form anhydride. Okay, both form anhydride. But see, let us see how is the condition will change. Number one is, if you take fumaric acid like this, okay, so on heating at around 403 Kelvin, just now we wrote now what will happen, water molecule is removed like this. So anhydride, malic anhydride will be written like this. Okay, CO and this is O. On the other side you have like this. This is called as malic anhydride. Understood? No, but under extreme condition only you will get the fumaric anhydride. So this is possible, but other one under the same condition it will not show. Are you clear? So they have similar properties but not exactly same. That means identical properties are not exhibited. Are you clear? Next one is stability. Third one is very important. So if you are observing the stability of the compounds, always the trans isomer are more stable compared to cis isomer. This you have to remember. Why it is so? What is the reason? Okay, you can take an example. Okay, so suppose you are writing like this, CH3 on the same side you take, all right, and on the other side you take H. This is cis form. How do you get the trans form? Methyl group is taken to this, and here you have CH3 and H and H. Both of you all clear with this? Are you able to understand the difference here? One example, simple example I took. The bulky groups are present on the same side. If the bulky groups are present on the same side of the double bond, what will happen? The steric hindrance is caused. Is it right? Understood? No. If you are having steric hindrance, what happens? This is electron releasing group. So imagine negative charge is distributed on this carbon. On the other side, this also will distribute. So what will happen? Due to this, there is a hindrance, or you can also say negative and negative will repel each other. Hence, there is a less stability. But here what happens? The bulky groups are far from each other. So the repulsions will be less. Hence, the transform will be stable compared to your cis form. Are you able to understand? Due to the repulsions between the bulky groups, the stability of cis form is less. Clear? Everyone understood? No difficulty in following this?
Yes, sir.
Okay, no? Fine. So next one you have discussed about this. Carbon double bond N and one more type is N double bond N are also exhibiting geometrical isomerism. Understood? So how it will be? First, let us take one example, benzol dioxide. Now you are not talking about cis and trans. What you will do is you will use a term called as a syn isomer, and second one is anti. Syn and anti isomers are observed if you are having C double bond N as well as N double bond N. Understood? No, it is not restricted between C double bond C. Okay, let us write. First one is aldoxime. So we will discuss in grade 12 oximes, that is aldehydes and ketones will exhibit this. Okay, so ketoximes, aldoxime as well as ketoximes will have C double bond N in this. First and foremost thing, I'll give you one structure. C6H5, that is phenyl group, is connected to C double bond N like this. And this is OH and this is H. Here you know very well you have lone pair of electron. Understood? No, this is lone pair of electron. Now on the other side, I can also represent this lone pair here and take OH here. Everyone understood this? Okay. So the phenyl group and hydrogen will remain the same, but what I have done is the lone pair and OH groups, okay, are exchanged here. Can we write like this? The aldoxam in which H and OH are on the same side, okay, this H and OH are on the same side of C double bond N, okay, then you call it as syn isomer, okay. Benzaldehyde with the oxime, so we call it as benzaldoxime. Okay, I'll show you how you will get oxime also, I will show. So syn benzaldoxime, now what happens, your H and OH are on the opposite side of C double bond N. Understood? Now we are talking about which structures here, H and OH. H and OH, they are on the opposite side. Hence you call it as anti-benzaldoxime. Okay, because we are talking about aldoxime, I'll show you. Suppose you take aldehyde in this way. Okay, this is CH3 group and this is H. Acetaldehyde you have taken. Plus NH2OH you take. Now, what is NH2OH? Hydroxylamine. Hydroxylamine. Is it right? Amino group was there or NH3 group is there. In that OH is substituting H. So leave that. Now condensation reaction, removal of H2O. Then what will happen? Keep this as such, CH3, C and H. This will become double bond. Now what is there? NOH is there, right? N-OH will combine to this. Then this is called as oxime. Clear? So what you took here, you have taken acetaldehyde. Right? Now this will be considered as acetaldehyde oxime. Same thing you did. You took benzaldehyde. Is it right? So dash C double bond O and H. So previous example I'm talking about. Benzaldehyde, if you treat with NH2OH, that is hydroxylamine, on condensation reaction, after condensation, you get this is benzaldehyde, right? So phenyl group C, and you got here double bond N OH, and this was H. Same thing. Okay, so can we write like this? This OH, if you take on the same side, you put now. Now which type of isomer? Syn. Clear? Understood? How did you get oximes? When you react aldehydes with hydroxylamine, you will get oximes. Same thing. Benzaldehyde with hydroxylamine has given you benzaldoxime. Okay, no? Next one. If you are writing, right, how do you mention the syn and trans isomers you have seen? Is it right? Clear? Any doubt you have? Yes? You can also like represent the ketones also. Okay, we can also show the ketones. How do you get the ketones now? If you write like this, the same way. Imagine this is CH3 and this is CH3. Okay, this is called as acetone. Now, if you react with hydroxylamine, NH2OH, Vaishnavi, tell me what happens now. Condensation means what you will remove. Is it okay? Water is removed, right? So what you get? C double bond N OH, and here it was CH3 and then CH3. Are you clear? So likewise, you can also form the oxime for this ketone. Okay. Next. One more thing is azobenzene. Right. So the example, phenyl with N double bond N, right, and second phenyl group is there. Now you know very well you have a lone pair and this also has a lone pair. If the lone pairs are on the same side or on the same side of N double bond N, then you represent it as syn form. So this is called as syn azobenzene. Clear? Everyone understood? Now how do you write the anti-azobenzene? Right? Clear? No? So this is one phenyl group. Now what you do? Take it to the other side. Now the question is the lone pair here and the second lone pair here. So what you have, if the lone pairs are on the opposite side, right, then you call it as anti. So this will be considered as anti-azobenzene. Clear? You're all able to follow? Right?
Yes, sir.
Now, one more important concept here. In the case of this cis and transform, just now we have spoken about steric hindrance or steric repulsions, whatever. So how do you identify the steric hindrance here? So you take the structure CH3, C double bond Z and CH3. Okay. So now you know very well, same groups are present on the same side of the double bond, and this structure you call it as a but-2n. Now the form is very simple, you know, cis but-2n. Now if you are writing the trans but-2n, what will happen? These two groups, you know very well, these are bulky groups, right? And also they are electron releasing groups, so they will send electron density onto these carbons. Is it right? On the other side, what will happen? CH3, C double bond O, and now the bulky groups are very far from each other, right? Understood, no? So when they repel each other, okay, this repulsion is known as this repulsions which you have is known as steric strain, or another name is van der Waals strain, or steric hindrance. Understood, no? So what is the name given to these repulsions? Steric strain or van der Waals strain, or in short, many times we use steric hindrance. If you have that, what happens due to the repulsions? This will be unstable. So reactivity will become less. But on the other side, if the bulky groups are far from each other, there will be very less strain, or there is no strain at all. Here there is no strain. There is no strain. Therefore, what will happen? This trans isomer is more stable. Okay, please understand the steric hindrance. Okay, why you will get the repulsions, all those things. Everyone clear? Understood this? Okay, I'll share the homework for you, and we will discuss optical activity. Okay, in the next class. Okay, Raghav, understood? Clear?
Yes, sir.
Okay. Okay, ma. Thank you.